Hello people, today we will be talking about protein secondary structure prediction. Now with this video we will be discussing about the scope of secondary structure prediction for proteins and why do we do this secondary structure prediction and what is the need for the secondary structure prediction, and then we will talk about what are the various methods that by which we do this structure predictions. Fundamentally, suppose if you are working on a protein and you discover a new protein sequence for a protein for which the functionality is unknown. So what we try to do is to find out some function that protein can perform, and for that we need some information regarding its structure and its functionality. Now if we have some proteins which are similar in the databases, so we can perform homology modeling and or homology based methods for function prediction and structure prediction. But if we don't have the proteins who are not, we have proteins which are not structurally similar with the proteins within the databases, then we have to derive their structures using secondary structure predictions. Now fundamentally in the secondary structure prediction we try to discover the 3D structure of their backbones of specific protein areas, which basically are the alpha helix, beta sheets and coils. Now the assumption is that the secondary structure of residuum is described by its amino acids in the given position, because the type of amino acid defines how it is going to provide steric stability with its neighboring amino acids. Now with this we have we can understand the similar structure like alpha helix, let's say, can be built up using various amino acid sequences. So if a structure can be represented using various sequences, we call it chameleon sequence, a sequence that assumes that different secondary structure depend on the fold context. Now what can be the type of structure that we are having in the secondary structures? So one of them is alpha helix, and it is the most abundant structure. It has around 3.6 amino acid per turn, and average length have 10 amino acid, which can vary from 5 to 40. The inner facing side chains are hydrophobic, and the third of every fourth amino acid is hydrophobic. The next structure can be the beta sheet as shown here. They depend on the hydrogen bonding between separated region of the chain. Each 5 to 10 amino acid at each region forms a beta sheet. Now there are parallel, same directional, anti-parallel bonds between these beta planes. Now the third structure is anything other than beta sheets and alpha helix. These can be turns, loops and coils. A turn is composed of 3 to 4 residues, forms sharp bend that redirect the polypeptide backbone towards the interior. A loop is similar with the turns but can form longer bends. Turns and loops help large protein fold into compact structure. A random coil is a class of conformations that indicate an absence of a regular secondary structure. Now, what are the methods that can predict the secondary structure for the proteins? Fundamentally, the Chow-Fasman method, Gore method, and nowadays we are using neural network methods for structural prediction. So, what is the accuracy of every method that we rely on and how they predict structure? When we fundamentally talk about the Chow-Fasman method, which was given by Chow and Fasman in 1974, the idea was to get a probability of particular amino acids in particular region of the secondary structure. The accuracy of this method is nearly about 50%. Then we can move to the conditional probabilities like Gore method, which was given in 1978, which gives an accuracy of around 60%. Then we have more improved algorithms and the neural network systems that provide you the information with secondary structure, and they provide you an accuracy about 70%. With the latest improvement, and the environment based studies, we can predict the secondary structure by 80% of its accuracy. Now let us first discuss about the Chao-Fasman method. In Chao-Fasman method, we rely on the propensity value. The R group attached to the protein is responsible for that particular propensity value. The main terms used in Chao-Fasman methods are alpha helix or beta sheet marker, alpha helix or beta sheet breakers, and propensity value. There are many online servers that can predict the secondary structure using Chao-Fasman method, and the statistical approach is based on calculation of propensities of each residuum to form alpha helix or beta strand. Now, what is propensity value? The propensity value is a probability value of a particular amino acid to lie in a particular structure. That is a tendency of amino acid to behave in particular secondary structures, say alpha helix or beta sheet. The propensity value of alpha helix can be determined as in the given formula, that is frequency of amino acids in alpha helix to frequency of residues in alpha helix. Then the alpha helix is made up of 20 amino acids, as we know, and the amino acid percentage present for 5 times, let's say 5. Let us assume that it's coming in 5 times. The frequency of amino acid in that particular alpha helix will be 5 of 20, which is 0.25. If the total residues in the protein is 100, then we can say the only 20 amino acids after the 100 are making alpha helix, then the frequency of residue in helix is 20 upon 100, that is 0.2. The same is applicable on beta sheets. Now the algorithm relies like this, given here. The actual algorithm for turn prediction consists of these following steps. First is to identify the band at residue number, let's say j, to calculate following values. The propensity value is determined by p at j multiplied by p j plus 1, j plus 2 and j plus 3, as you can say. Now where fj plus 1, j plus 2 and j plus 3 are the band frequencies in the 4th position of that particular beta term. If the propensity value is more than 0.00075, then we can say that the particular residue can exist there. Now the Gore method. The Gore method assumes that amino acids up to 8 residue of each influence secondary structure for central residue. So like 4 amino acids from the central residue on the other side and 4 on other side. The program is now in its 4th version, which is Gore 4, and the accuracy of Gore when checked against its set of 267 proteins is 64%. This implies that 64% of the amino acids that were correctly predicted being in the helix, coil or sheets. The algorithm used sliding window techniques of 17 amino acids. Now the algorithm which uses this sliding window techniques means like they switch between the amino acid range in the set of 17. The site of amino acid sequence and alignment is determined by the predict secondary structure of central sequence. The good for helix than sheet, because beta sheets are more inter-sequence hydrogen bonding, because they are more dependent on inter-sequence hydrogen bonding than intra-sequence molecular bonding. Then it has a 36.5% accuracy for beta sheet, and let's say the input any amino acid sequence and it gives an output which is a secondary structure. So what are the improvements that have been in the Gore thing? Now you can set your sliding windows from 12 residues, from 6 residues to 12 residues. So you can lock it from 6 to 12. Now if the threshold value is more towards, if the threshold value is more if the calculated value is more than the threshold value, then we can say that particular amino acid lie in a particular secondary structure, say alpha helix or beta sheet. Now, neural networks, they are the most effective structures prediction tool for pattern recognition and classification. The protein sequence is translated into patterns by shifting a window of n adjacent residues through a protein sequence. Now, there are various methods by which we can do it. The details for these methods are beyond the scope of this presentation, but we can discuss it in another video. The methods are given here, like hierarchical neural network, or NNPredict, Cypred, or GenThreader, Cyblast, etc. Other than this, we can use multiple alignment based on self-optimization method. One of the tools is SOAPMA, which can predict around with accuracy of 69.5% for amino acid for 3-state description of secondary structure, with comparison to whole database containing 126 chain of non-homologous protein. Another tool which can be used for prediction of secondary structure is hidden Markov model, where each residue has a probability with their hidden state, which are alpha helix or unstructured beta sheets. So hidden Markov model means that the state is directly invisible to the observer. It provides a description of what PFAM provides. Now, each HMM is trained for sequences of protein for particular structures. Now, models are used to predict those queries for their secondary structure. So these are the references that I took. Thank you.